Hi everyone. So we are jumping into chapter 2 today, and chapter 2 is all about a topic called variation. Variation is a type of relationship between variables. It is a function relationship, which was sort of our focus of chapter 1. Variation has some other properties to it, and there's different types of variation we can talk about. So the simplest form of variation is just direct variation. That's the first thing in your notes packet for chapter 2. So without further ado, we'll go ahead and get started on this topic. Sorry about that. Need to make my face go away. Okay, so variation. Just in general, variation is a relationship between two variables. And I think for today, we're just going to leave it at that. There's some other things that we're going to learn about variation, but for now, this is all we need. And so as an example of what I mean by direct variation, I'm going to kind of just put this here. So first of all, I don't think you need to copy all of this down. In fact, you might not even need to write it down at all. I'm kind of just trying to make a point about what I mean by variation. So pop can refunds, okay? You get 10 cents per can. So we could set up an equation for that, and we could say our refund is equal to 10 cents per can. This is a variation relationship where when I change how many cans I get, that also changes my refund, okay? So using this relationship, I want you to think about what's going to happen to your refund if you triple the number of cans, and then what's going to happen to your refund if the number of cans gets cut in half. You'll probably have a question pop up in just a second on that. Okay, so hopefully you came up with, if your number of cans triples, then your refund triples. And if your number of cans cuts in half, then your refund cuts in half. Okay? And so one of the characteristics of direct variation, so this is not all types of variation, but direct variation. I'm just kind of jotting this off to the side, is that when one variable increases, the other variable increases as well. Okay? So that's important to know that with direct variation, your variables are linked in a way that when one gets bigger, the other one gets bigger. And in simple direct variation, which is really what we're talking about today, in simple direct variation, the relationship is exact. So when this triples, this triples. When this cuts in half, this cuts in half. We're going to throw some exponents at you, and I actually don't remember if that shows up in this lesson or the next one. That's going to change that a little bit, but for right now, that's what you need to know. You will want to make sure you mark down this sentence. Remember there was a sentence with function relationships that I had you write down, and it was really important. This is important too. So in this particular example, we would say the refund varies directly as the number of cans, okay? And so if I wanted to write this a little more generally, I would say the dependent variable varies directly as the independent variable. Okay, so probably this one is actually more important to write down than the refund one. Okay, so, and this sentence structure is going to show up in just about every variation problem we do. Okay, so when we do direct variation, we can always write an equation in this form. We would say y, which is our dependent variable, is equal to some constant times x. So this is like a number, a constant. Okay, and that's what direct variation is when the two variables are linked in a way where one is just another one being multiplied by a number. Okay? And then x, sorry, I should have drawn my line here. X here is my independent variable. Okay, so let's take a look at this first example. The weight of an adult animal of a given species is known to vary directly with the cube of its height. Okay, so we are getting into some exponents here. I couldn't remember if that was this lesson or not. And so again, do you see that sentence structure in here? You see it varies directly with the cube of the height. So write a general equation relating W and H. This lays out the same way every single time. So we're going to start with our dependent variable, which is at the beginning of the sentence. The weight is equal to K times, there's always going to be a K. There's always going to be a multiple in there. And we're not actually using any numbers in this problem, which I know makes it confusing, but there's always going to be a multiple of K. Okay, when you're doing direct variation. So the fact that it's direct means that we're multiplying by K. And then the cube of its height, I would write as H to the power of 3. So this right here is what we refer to as a general variation equation. Okay. And then it says identify the independent and dependent variables. Well, if we compare this sentence with this sentence that I wrote up here in pink, that should be easy to do. The weight is the dependent because it's the one that varies directly with something else. And then the height is independent. And think about that. That should kind of make sense to you, that the weight of an animal depends on how tall it is. Okay? So this is really just all about this is sort of the first step of a variation equation. I'm sorry, I'm stumbling all over words today. This is always your first step in setting up a variation problem, is writing this general equation. So that's sort of what we're practicing. And it always comes straight out of this sentence. So the weight varies directly. That tells me K times the cube of the height. That's H cubed. Okay? Okay, let's move on to example 2 then. So this is sort of the type of problem you're going to be seeing, like on your homework tonight. And I've broken this down into 4 steps here. Your homework problem won't necessarily break it down into those 4 steps, but you need to know those 4 steps, okay? So these same 4 steps is what you do anytime you reach one of these problems. So let's see. A certain car needs 25 feet to come to a complete stop after the brakes are applied at 20 miles per hour. Braking distance varies directly with the square of the speed. That's your magic sentence, and I'm even going to highlight that. It's directly with the square of the speed. Okay? That's the sentence that you need to set up this general equation. Okay? So before I start working with any numbers, I need a general equation, which is sort of like a formula. Okay, so braking distance. It tells me it wants me to use D to represent braking distance. Varies directly, so that's K times square of the speed. So square of the speed means that's going to be S squared. Okay, so that's my very general formula. Now, the thing is, if I'm going to actually want to use numbers in this problem, if I'm going to want to put numbers in, I need to know what this magic multiplier is. And every problem, every situation has a different magic multiplier. So I need to find out what K is. Okay? Well, it gives me 2 values that I could plug into my formula to figure out what K is. It gives me a distance and it gives me a speed. So, and almost every one of these problems does that exact same thing. It gives you 2 values that we already know. So I'm going to use those 2 values to solve for K. I'm going to plug in 25 for D, and I'm going to say K times my speed squared, so that's 20 squared. And now I just want to solve this. I want to figure out what K is equal to. Okay, what's this magic multiplying factor? So 20 squared is 400, so I'm just going to rewrite this as 25 equals 400K. And then just be careful about which one you're dividing by, because sometimes it's not what you think it is. Okay. And then 25 divided by 400, oh, let's see, that's going to be 1 out of 16, I believe. Okay, so my K value is 1/16. Okay, so step 3, I'm going to rewrite that general equation, but now I know what the K value is. So I'm going to say now my equation is really going to work like this, 1/16 times S squared. And now I can use this to find any combination of numbers I want. Okay, so this now applies to any distance and any speed I can come up with. So now it says evaluate the function, and when I say the function, I mean this, for the given value of the independent variable. Well, here at the end of the problem, now it wants to know how much distance would I need if I'm traveling 60 miles an hour? Well, that's a speed, so I'm going to plug that in for s, 1/16 times 60 squared, okay? And then I'm just going to evaluate. I'm going to do 1/16 times 60 squared. I'm going to show you that because I think some of us are still kind of struggling with how this would go in a calculator. Except I don't know where my good calculator is. Let's see, you're going to have to just deal with the junk on the screen there. But okay, so to type this in, I would do 1 divided by 16 times 60 squared. Okay, this ANS thing and all this junk. My clear button in this calculator doesn't work, so ignore all that stuff up above it. 1/16 times 60 squared is 225. And so to answer my question, at 60 miles an hour, I would need 225 feet to come to a complete stop. So again, these 4 steps are what we're going to be using all throughout this entire chapter when we're doing these variation equations. And I think the very first thing you need to do in every one of these problems is identify this magic sentence, okay? Because that's kind of what gives you the form, and then you plug numbers into that, you solve for k, and then you evaluate the function for whatever value they actually gave you, okay? Okay, that should be enough to get you going on homework for today. So your homework is out of the textbook from section 2.1. Make sure you answer the questions posted here, and then do a good job on your homework assignment, and we will go over this in class some more tomorrow.